In this video, we're going to go through several problems involving continuity. First off, let's remember the definition of continuity. A function f of x is continuous at x equals a if and only if the limit as x approaches a of f of x is equal to f of a. Meaning, as we approach a from either side, the y values of f of x are approaching the point at x equals a and y equals f of a. So, looking at example 1, they give us this graph f of x. In part A, they want us to find the x values of each discontinuity. In each case, explain the discontinuity in terms of the definition of continuity and classify each discontinuity as removable or non-removable. So if we take our pen and start tracing the curve, we notice that we have to pick it up here at x equals -3 and then put it back down there. Pick it up again at x equals -2 and put it back down like that. Pick it up again at x equals 0 and pick it up again at x equals 4, like that. And so that means we have discontinuities at x equals -3, x equals -2, x equals 0, and x equals 4. Now, if we look at the limit as x approaches -3 of f of x, we notice that when we approach -3 from the left and approach -3 from the right, we're getting two different values. So this limit does not exist, which means it cannot equal +5, which is f of -3. This is a non-removable discontinuity. Now, looking at x equals -2, we notice that again, the limit as x approaches -2 of f of x does not exist. And also, the function is not defined at -2. This is also a non-removable discontinuity. At x equals 0, again, the limit as x approaches 0 of f of x does not exist. When we approach 0 from the right, we get 3. When we approach 0 from the left, we're getting -2, and those are not equal to each other, so the two-sided limit does not exist. That cannot equal 3, which is f of 0. So again, this is a non-removable discontinuity. Lastly, let's look at x equals 4. When we approach from the left and from the right, that limit as x approaches 4 of f of x is equal to 1. And notice that f of 4 is equal to -4. And those two are not equal. And this ends up giving us a removable discontinuity. Now, in each of these 4 cases, we kept going back to the definition of continuity. And in each case, we saw that the limit as x approaches our value a of f of x was not equal to f of a. Part B, at which discontinuities, if any, is f of x continuous from the right? So for continuity from the right, we need to show that the limit as x approaches a from the right of f of x is equal to f of a. Basically, what that means is that a portion of the graph, when we're traveling from right to left, is going to reach an endpoint. And so one place where this happens is at x equals 0. At x equals 0, we have the limit as x approaches 0 from the right of f of x. That's approaching 0 here. The y values are approaching 3, which are exactly the same thing as f of 0. We also have this happening again at -6.5 Notice that the limit as x approaches negative 6.5 from the right of f of x, that appears to be negative 3, which is the same as f of negative 6.5. So those are the two places where our function has discontinuities, but the function is continuous from the right. Let's do this again, but this time we're looking for a discontinuity where we have continuity from the left. Well, that means we have to show that the limit as x approaches a from the left of f of x is equal to f of a. And the only place where we see this here is at x equals negative 3. Notice that the limit as x approaches negative 3 from the left of f of x is equal to 5, which is the same as f of negative 3. Example 2, determine the points, if any, at which each function is discontinuous. Classify any discontinuity as removable or non-removable. Each of these functions is going to be continuous on its domain. So you can think of this problem as simply asking for those points that are not in the domain of the function. Now with part A, f of x equals 2x over 6x squared plus 5x minus 6, we notice that we have a rational function, and we're going to go ahead and factor the denominator and figure out which x's make that denominator equal to 0. So the domain of this function is all real numbers, except for where 3x minus 2 equals 0 and where 2x plus 3 equals 0, which will be x equals 2/3 in this case and x equals negative 3/2 in this case. This function has vertical asymptotes at each of these locations. So we have non-removable discontinuities at x equals 2/3 and x equals negative 3/2. Part B, g of x equals x plus 2 over 2x squared minus 8. Again, let's go ahead and factor. This time we notice that we have a factor of x plus 2 that cancels. That means that we have a discontinuity at x equals negative 2, but it is a removable discontinuity. When we get this cancellation here, that means that we have a hole at x equals negative 2. On the other hand, when we don't get cancellation, that's where we have a vertical asymptote. So we have an infinite discontinuity. In this case, we're just going to say it's a non-removable discontinuity at x equals 2. Part C, h of x equals x over 3 minus e to the x. Again, we're going to see where the denominator equals 0. And that's going to be when e to the x is equal to 3. Of course, we want to solve this for x, so we can take the ln of both sides to get ln e to the x equals ln 3. ln e to the x is just plain x. So we've got a vertical asymptote at ln of 3. So we have a non-removable discontinuity at x equals ln of 3. Part D, c of x equals cotangent of pi over 2x. Now, the basic cotangent graph is undefined at x equals pi k, where k is an integer. If you need to, pause the video and review your trig graphs. In particular, you'll notice that the cotangent has vertical asymptotes at 0, at pi, 2 pi, and at negative pi, negative 2 pi, and it goes on in both directions forever. So now we can take this information and just notice that if we allow the argument pi over 2x to equal pi k, where k is an integer, and solve for x, basically multiply both sides by 2 over pi, we're going to get x equals 2k, where k is an integer. So c of x has non-removable discontinuities at x equals 2k, k is an integer. Example 3, decide if the function is continuous at the given points. If it is discontinuous, classify the discontinuity as removable or non-removable. Part A, f of x is equal to x squared minus 1 over x squared plus x, and we're going to check x equals -1 and x equals 0. Let's go ahead and factor the numerator as a difference of squares, and the denominator factoring out the GCF x. We notice immediately that the factor x plus 1 is going to cancel in the numerator and denominator. And if you remember, that means there's a hole in the graph of f of x at x equals -1. That means that we have a removable discontinuity at x equals -1. On the other hand, the factor x in the denominator does not cancel in the numerator. This means that we have a vertical asymptote at x equals 0. In other words, we have a non-removable discontinuity at x equals 0. Part B, g of x is the piecewise defined function, which will be the absolute value of x plus 2 if x is less than 1, and will be 2 plus the square root of x minus 1 if x is greater than or equal to 1. And we're going to check for discontinuity at x equals 1. So again, recall the definition of continuity. We need the limit as x approaches a of g of x to equal g of a. So first, if we're going to look at the limit as x approaches 1, because g is defined differently on either side of 1, we're going to start with one-sided limits. In other words, we're going to start with x approaching 1 from below of g of x and compare that with the limit as x approaches 1 from above of g of x. If we're approaching x from below, then we'll be using the absolute value of x plus 2 for g of x. If we're approaching 1 from above, we're going to use 2 plus the square root of x minus 1, like this. Direct sub gives us the absolute value of 1 plus 2, which will give us 3. Here, direct sub gives us 2 plus the square root of 1 minus 1, which will be the square root of 0, which, when added to 2, gives us 2. So our right-hand limit and left-hand limits are not equal to each other. That means that the two-sided limit as x approaches 1 of g of x does not exist. And if this limit doesn't exist, there's no way that it can equal 2, which is g of 1. What we have here is a jump discontinuity. We'll classify this as a non-removable discontinuity. Looking at part C, we again have a piecewise defined function. And notice that we're doing something different for x is less than -2 than we are for x is greater than -2. And when x is equal to -2, we get 0. So again, we're going to need to check the limit of h of x as we approach -2 from the right and from the left. As we approach -2 from the left, h of x is defined as negative of x plus 3 quantity squared plus 4. But as we approach -2 from the right, h of x is defined as -1/2 x plus 2. Direct sub will give us 3 here, and here direct sub will also give us 3. So this means our two-sided limit of h of x as x approaches -2 is equal to 3. However, this does not equal 0, which is h of -2. This means that the graph of h has a hole at x equals -2, and the point at x equals -2 is 3 units below where the hole is. So this is a removable discontinuity. Example 4, find the value of k that makes the function continuous over its domain. And here we have f of x is equal to the piecewise defined function kx plus 1 if x is less than 3, and kx squared minus 1 if x is greater than or equal to 3. To be continuous at x equals 3, we need the limit as x approaches 3 of f of x to equal f of 3. Well, for the limit to exist and equal a specific number, that means the right-hand limit and left-hand limit have to equal each other when we plug in 3. In other words, kx plus 1, if I put in the 3 for x, would look like this. That's going to have to equal kx squared, plugging the 3 in for x, minus 1. In order for the limit to equal the value of the function there, these two expressions have to be equal to each other here. So that's 3k plus 1 is equal to 9k minus 1, which will give us 2 is equal to 6k, so k is equal to 6 over 2, or 1/3. Example 5, use the intermediate value theorem to show that there is a root of the equation -x squared minus 5x plus 3 equals 0 in the interval -1 to 1. So let's first give this a name. Let f of x equal -x to the 4th minus 5x plus 3. And notice that f of -1 is going to equal 7, and f of 1 is going to equal -3. You can pause the video and double check those. So f of 1 is less than 0, which is less than f of -1. In other words, n equals 0 is a number between f of 1 and f of -1. Now, f of x is a polynomial, and polynomials are continuous everywhere. Now, basically what the intermediate value theorem says is that we have values here. There's my -1 and my 1. At -1, our graph was way up here at 7. And at +1, we were over here at -3. And our polynomial is continuous. So that means it's got to hit every single y value between f of -1 up here and f of 1 down there. In particular, it has to, in this case, cross the x-axis, right? And so this is some number c in the interval -1, 1. So by the intermediate value theorem, there exists a c in the interval -1 to 1 such that f of c equals 0. In other words, f has a root in the interval -1 to 1. Go ahead and do the similar problems that come after this, numbers 1, 2, 3, and 4.